because we realize that this is a constant and this Ry depends only on one variable, then we deduce from here that also y of t is wide cell stationary. And so we said a wide cell stationary input through an LTI system produces a wide cell stationary output process. Okay? And finally, we realized that because of all this convolution, it's best if we work in the frequency domain, and so we define also this quantity Sx of omega as the Fourier transform of Rx of tau, or of t, doesn't matter, okay? And from all these results, we got the following, that Sxy of omega is Sx of omega times evolution in the time domain becomes a multiplication in the frequency domain, h star of j omega here, and S of and Sy of omega is Sx of omega times h of omega magnitude squared. This is very important formula. We call this quantity the power spectral density PSD of x of t, and really this is the PSD of y of this process. So what is the power spectral density of a wide cell stationary process? Is defined as a Fourier transform of its correlation function. Okay? But the word power spectral density in itself hints at some interesting interpretation. So I want to give now an interpretation of what this Sx of omega is. And I will give this interpretation through the following examples. So what is the physical meaning of the power spectral density? Alright, so recall, let's go back to basic things. What is an instantaneous power of a signal, or actually a voltage or a current? Now you know, if a voltage is attached across a resistor, then the instantaneous power of that resistor that is dissipated as thermal energy is what? Let's say if V of t is across the resistor, at least electrical engineers should answer that. What is the instantaneous power? Instantaneous power. Say?
V squared over R.
V squared of t over r. Okay? So, and if it was a current, I of t here, then it would be also I squared of t times r. So the instantaneous power is a quantity that changes with time, right? Depending on the voltage or current applied to that resistor. But what is important here is that if the signal of interest is V or I, then we take power to be the square of that. So every time I give you a random process x of t, now, which is a random signal, say t in R, then I can say that xt magnitude squared is complex, or xt or xt squared can be thought of as instantaneous power. Yes? Let's define this as instantaneous power. Okay. So let's go back now to determinism. How do we find the power P of a signal? Well, if the instantaneous power is something that's changing with time, then we can say that the power of the signal can be thought of as the instantaneous power integrated over a window that gives you the energy over a window of time to t, but power is energy over time, so I subtract with that time, and then because I don't know what t is, I take the limit as t goes to infinity. Okay? So minus e to t is the energy. Remember, this is the square, not x, it's the square of that. So this is how the definition of the average power of a signal. of x of t. Okay, the signal x of t. If I go and do the same thing for random processes, I will have a problem. Because then I will say the power of x is limit as t goes to infinity, and I don't discuss the limits of random processes yet, we will, of 1 over 2t, integral from minus t to t, of x of t squared dt. What is the problem that I'm facing here? If I want to define this as the average power of the random process x.
X of t is a random variable.
X of t is a random process in general, right? That evolves in time. So if I integrate it, it's still some kind of random variable. So this thing is a random variable because it's a function of this random process. Okay? So someone asks me, what is the average power of your random process? I don't know what to say, it's a random variable. So for that reason, we define actually for random variables the power as the expectation of this. Okay? So that's our average power. Okay? Now let's try to see how to find this. I will do a little bit of magic here. I will push the expectation inside the limit. Now this is fine for engineers, but mathematicians will have a big problem. In fact, there's a whole theory in math called, measure theory that tells you when you can do that. Okay? The whole measure theory tells you exactly when to exchange these two operators. Okay? But once I push this inside here, then the rest is easy. I can push it inside the integral because of linearity of expectation, and it always will apply there. So let's see. This is going to be the limit, as t, I put a small question mark here, as t goes to infinity, suppose we can do it. 1 over 2t, integral from minus t to t, mean of x of t, and let's say everything is real, so x of t squared dt. Okay? What can I say about mean of x of t squared? Can I relate it to the correlation function of x? Suppose x of t is White's stationary. What is the mean of x of t squared in terms of the autocorrelation function?
Would that just be Rx of 0?
Rx of 0, of course. That would be Rx of 0. Recall, Rx of tau is mean of x of t plus tau, x of t. See, t doesn't matter here. What matters is only the difference between the two samples, right? So at tau equals 0, this is x of t times x of t. Okay? So that's Rx of 0. And now everything boils down to Rx of 0 is constant, so I take it out of the integral. The integral gives me 2t, limit everything goes, so I get Rx of 0. Nice! So I know that the average power is Rx of 0. Okay? But what is Rx of 0 in terms of S of x? What is the relationship of this with Sx of omega? In Fourier transforms, if I have a signal x of t and its Fourier transform x of omega, then the integral minus infinity to infinity of x of t dt is what? Substitute omega equals 0 here. That's 1. Okay? So, in other words, the average value in some sense of the signal is the DC component, which is x of 0. Okay, so this here says that this is integral, minus infinity to infinity d omega. There is 1 over 2 pi here because I'm using omega instead of f, but don't worry about it. Okay? So, look what happens here. The average power is the integral from minus infinity to infinity of this quantity. Okay? And in the same way that mass is the integral over volume of the density, right? In the same way, that quantity now can be thought of as the power density spread over frequencies. Did you see the analogy? Here, this quantity, whatever that is, the mass density of an object, if you integrate over its volume, it gives you its mass. Similarly here, this quantity, if you integrate it over frequency, it gives you its average power. So if this is mass density, or volumetric mass density, this should be spectral power density. Well, we call it power spectral density. Make sense? Okay. So if you integrate over all omega, it gives you this one might say, one might add the following. What if I want to find the power of my signal x of t, or my random process x of t, that is contained within a specific range of frequencies? So, how much power does x of t have in the range omega in, let's say, omega 1 to omega 2. How can I measure that? So I have this x of t variance sequence, but I want to measure its power over only a certain frequency range. Here's what I can do. I can filter out all other frequencies from x of t, and then measure the power of the resulting signal. So I'm suggesting I will take x of t, random process, put it through a LTI system, which is actually a band pass filter, which has frequency response function. We know that it has to be symmetric, W1 to W2, that's omega, right? Minus W1 times W2. And then I will get another process y of t. And then I will measure the average power of y of t, right? And this is the same as, the average power of the whole y of t is the same as the power of x of t within this range. Yes, because I have eliminated all other components of x of t. Make sense? Let's do it. So what is Py? Well, by definition, is the integral minus infinity to infinity, 1 over 2 pi, of Sx of Sy of omega d omega. But what did we just learn last time? That any process through a filter produces a power spectral density at the output, which is equal to the input power spectral density times the transfer function squared of the filter. So this is going to be, if this is my h of j omega, of h of omega, right? Then this is the 1 over 2 pi, integral from minus infinity to infinity, Sx of omega times h of omega norm squared d omega. Okay, but what is that? Well, h of omega is just 1 between omega 1 and omega 2 and 0 elsewhere. So this is 1 over 2 pi integral over all omegas such that this is between omega 1 and omega 2 of Sx of omega d omega. And this gives me one more physical meaning for the power spectral density of the signal. Because the power of y, by definition, by this experiment that I constructed, is nothing else but the energy or the power of the signal x within the frequencies omega 1 and omega 2. And how do I find that? Just by integrating over the region of interest, omega 1 to omega 2, the power spectral density of my signal. Okay? So that's why we call it power spectral density, because it tells you how much power, is allocated at different frequencies. Yes?
Why do we care about power according to frequency? So why do we care about?
Why do we care about this, you say? Well, as engineers, we care because this is why, I mean, the same question could have been put as follows. Why do we care about Fourier transforms? If we know the signal x of t, why do we care about x of j omega, right? We care because we're interested to see the same object, x of t, the same signal, both from the time domain and from this frequency domain. Sometimes when we design filters, it's best if we design them by looking at the spectrum. Because we want to design filters, let's say, that cut some frequency band and amplify some other frequency band. Okay, so it's useful. Okay. Is that, you don't believe me it's useful? You're not convinced?
I do, but I'm not convinced.
You're not convinced that looking at the signal both from the time domain and the frequency domain is useful?
I agree with this, but I don't see how this is connected with your and the probability.
It's not yet connected to probability, you're right about that. But it tells you something about the random process. See, in our undergrad years as engineers, we learn how to deal with deterministic signals and we come up with, Fourier transforms and all that. But most of the signals that we actually process in real life are not deterministic signals. See, nobody cares to measure a sensor which is a deterministic signal. If it was a deterministic signal, then I wouldn't want to sense anything, right? I would know it. Everything is random. So somehow I have to develop a similar theory of Fourier transforms, of autocorrelations, of power spectral densities for random signals. So you can think this as a bridge between what you know for deterministic and what you know for random signals. Okay? You're right, there's no probability in here. Okay? But I'll get back to you and show you that there is a lot of kind of hidden gems in here. Some things that you would not be able to see otherwise unless you look at the frequency representation. Okay. Other questions regarding this development? What is power spectral density? Yes?
Not exactly on this, but in terms of real life applications, how often are our signals wide sense stationary?
Very often. Very, very often. This is the standard assumption.
Okay.
Okay? You talk to your cell phone. It receives signals which are the signals that are sent by the transmitter, like bits, zeros and ones, and noise is added to that. Noise is assumed to be wide sense stationary process because the noise doesn't change with time. Now the signal intensity might change with time, okay? Because you get into a tunnel or something like that and there is fading. But the noise component, because it's generated usually inside your electronics of your device, because there are passive elements there, this doesn't change. So this is a standard example of a wide sense stationary process. Okay? So we can trust that this is not some kind of academic discussion. In fact, if anything, this is one of the most practical things people use 501 for, okay? To study this type of processes in and out of LTI systems. I want to show you a demo. Okay, so let's see some examples. Have you heard the term white noise? So white noise is a wide sense stationary process, x of t, where mx of t, of course, is mx, is 0, 0 mean, and rx of tau is delta of tau with some constant. And if this is true, and I take the Fourier transform, what is Sx of omega? Can someone tell me? This is a constant, don't worry about it. What is the Fourier transform of a delta function? 1. Okay, so this is n02 for every omega. Okay? So let us understand what is the meaning of that. This says that in the same way that white light contains all possible frequencies in equal power, this noise contains all possible frequencies, that is, this power is spread over all possible frequencies equally. That's why we call it white noise. What about that? Okay, what about that? What does that say? For all practical purposes, you can think of Rx of tau being 0, except at 0. That means, if I take two samples of that process, one at t and the other at t plus tau, this and that, these are two random variables, xt and xt plus tau. What will their correlation be according to that? 0. Let me add an assumption here, just for fun, that this is a Gaussian process. So if the two Gaussian random variables are uncorrelated, they are also independent. So these two samples that differ by tau, they are independent. Okay? You expect that a process where the two samples are getting closer and closer to each other, there is some dependence between them, right? But what happens for this process? No matter how close you take these samples, as long as they're not the same samples, they are completely independent. This is a very fast varying process. It decorrelates immediately. You see? That's why it has to contain all these frequencies. Because a lot of frequencies, high frequencies, contribute to a very fast varying process. That's the model that we try to capture. A process that decorrelates so fast that its correlation is zero everywhere, no matter how close the samples are. Except, of course, when the sample is the same, in which case, something weird is happens. Rx of 0, recall, this is infinity, but Rx of 0 is mean of x of t squared. So this is an infinite power process. Okay? That's why it's not a practically realizable process. Okay? Because its power is infinite. You can see it here, because the power is Rx of 0, or there, because the power is what? How can I find the power from this diagram? From the power spectral density. By integrating out this, but this is infinity. And so really, truly practical white noise is more like something like that. Okay? But this frequency is so large compared to the system that we want to build that we don't care about it. Questions? Have you seen white noise? Ever? Here it is. That's white noise, as close to white noise as you can get. That's a kind of a simulation program for signal processing. Okay? That's the time domain. Okay? It's a random process, right? It moves. In the frequency domain, that is power spectral density is this. As flat as you can think of a random process. Okay? The power spectral density is flat. Okay? Why is it that I can only see frequencies from minus 50 kilohertz to 50 kilohertz? This has to do with the fact that my simulation program works with a sampling rate of 100 kilohertz. So as you know from Nyquist theorem, if you have a process or a signal of bandwidth W, then you have to sample it at twice as fast, right? So I can only think of minus 50 to 50 as my useful bandwidth, since I'm sampling at 100 kilo samples per second. Okay, what if I take this process and I pass it through, look at this, a low pass filter, some LPI system, okay? What will I get? I will get a filtered noise. That's this. This doesn't look like changing so fast. You see that? Okay. What is its power spectral density? That one. Okay? This is nothing else but Sy of omega equals Sx of omega times h of omega magnitude squared. This is 1, it's constant, and so what you see here, this red curve, is nothing else but the frequency response function of my filter, which is a low pass filter. You see why? All frequencies around 0, negative or positive, you don't have to worry about the negative side, are more or less undistorted, but all these are suppressed. Okay? So that's what a color noise looks like. Okay, this is a color noise. Questions? White noise versus color noise. Any questions? No? Okay. So I want to revisit a problem that we have looked at in the context of random vectors. So let's revisit the simulation problem. What was the simulation problem for random vectors? I give you a random vector with zero mean and covariance matrix equal to the identity matrix. We call it white. And I want to generate a linear transformation, y equals ax plus b, or an affine transformation, to generate a new vector y that has a given mean and a given covariance matrix. Do you remember how we solved this problem? Roughly. We wanted to find what A is and what B is. Roughly. Do you remember roughly? Can you give me like the broad strokes? What did we do to solve this problem?
Do the expectation on both sides of the equation and then solve.
Yes! We found mean of y, which is A, mean of x, plus b. This was 0, so we equated that with that. And then we find the correlation, or the covariance matrix of y, which was, do you remember what was this function? The correlation function of y, based on that? A, correlation function of A transpose. Which was, this was A transpose. And do you remember how we solve for A? Okay, please tell me something that you remember. Let me just see. How did we solve this problem? How did we find an A such that when I multiply A transpose gives me a known covariance matrix?
Eigenvector of.
Yes! We broke C of y, we factor C of y through the eigenvector eigenvalue decomposition, right? We found its eigenvalues. So otherwise it would be a very difficult problem to solve. You agree, right? So we had somehow split it, and this eigenvalue eigenvector decomposition of C of y was very important in solving this problem. Okay, so hold that thought, and let's revisit this problem in the continuous time. So suppose I have a sequence x of t, a random process x of t, continuous time, which is white and stationary, and I say that it is zero mean, and cx of t is delta of t. So it's actually white noise. Okay, it's covariance matrix, which is actually equal to the correlation matrix here, is white noise. So I take white noise, and I want to generate another process y of t, okay, which has some given mean of y, and some given covariance function cy of t. So these two things are given. And I suggest the following idea. Take x of t, pass it through some LTI system to be found, what this impulse response is, add some constant b, and you get your y of t in here. Let's call this output yt prime, and this is going to be y of t. Okay, so I suggest this will solve the problem. Let's see why. Okay. What is mean of y of t? We want it to be my, right? But mean of y of t, by definition, is b plus mean of that. But mean of that is mean of this, mx, times h of 0. Correct? Which is nothing else but the integral from minus infinity to infinity, h of t dt. We found that last time. But what is m of x? Is 0 by the problem. Okay. So from here we get my equals b. Okay, we found that b. It has to be equal to my. Now what about h of t? How will I solve this problem? What did I do here? I calculate the covariance of y. So here I will calculate the covariance function of y. Well, whether I calculate the covariance function of y or y prime is the same thing. So let me calculate the covariance function of y t, which is the covariance function of y prime of t, which is, as we have seen in our review, the output of the filter has correlation or covariance, which is looks like that. So it's going to be the correlation function or covariance function of x convolved with h of t convolved with h star of minus t. Now what is that? The covariance function of x, according to the problem. Delta, that's good. So what happens when you convolve a delta with a signal? The signal itself, okay? So this gives me h of t convolved with h star of minus t. Put that in a box and ask yourself, how am I going to solve this problem? I'm given the left-hand side, I'm asking what the right-hand side is. I want to find one filter h of t, such that when I convolve it with itself, or not exactly with itself, but flipped around, it will give me a known covariance function cy of t. Think about this problem, and in the back of your mind, think about this problem. Look, they're kind of the same. I wanted to find a matrix, there I want to find an h, such that when I do this weird operation with these matrices, A multiplication with A transpose, that's a weird operation between H and H star, right? Convolution with minus. It will give me a known matrix. Well, it will give me here a known function. Over there, what helped me solve this problem? The eigenvalue decomposition. So somehow the eigenvalues of this matrix are important. What will help me solve this problem? The Fourier transform. Or you can say there's some kind of an eigenvalue, eigenvector decomposition of this function. Well, it turns out that the Fourier transform is exactly that. So if I take Fourier transforms here, I will be able to solve this problem very easily. So take Fourier transforms. What is the Fourier transform of Cy? Is Sx of omega. Right? That's by definition, the power spectral density. And what is the Fourier transform of the convolution of two signals? The multiplication of h of omega with h star of omega. So this is h of omega magnitude squared. So here in the frequency domain, everything becomes very simple. The filter that will do the job for you, that is, that will simulate this process, is a filter that has magnitude, h of omega, equal to square root of sx of omega. You might say, wait a minute, can I take the square root of sx of omega? In the same way that this had always real and non-negative eigenvalues, you can easily show that Sx of omega is always a non-negative function. Why? Well, if you go back here, that's actually a very simple thing to check. Remember we said that if you pass x of t through a very simple, through a filter like that, you will get the average power of the signal. So imagine that this filter is so narrow that only catches a very, very narrow sliver, let's say, of the frequencies, here and here. Then, if I measure this power, then I will get that the power of y is Sx of omega d omega over that range, if this was like a small d omega here, right? But since power is always a number greater or equal to 0, this is always a power greater or a number greater or equal to 0. So, long story short, power spectral density is always a positive number. So I can take its square root, so I can solve this problem. And you might say, well, just defining the magnitude of a signal is not giving me the signal itself, right? You can add any phase you like, okay? So you can make it maybe causal, maybe phase, all this nice stuff. And so from here, you can derive what h of omega is. You can pick h of omega, and then if you want to Fourier transform it, you get h of t. Okay? So what I'm trying to say here is that in the same way, when we dealt with matrices, the covariance matrix had certain properties like symmetry, non-negative definiteness, and the eigenvalue eigenvector decomposition was very useful in solving problems like that. In the same way, and I'm answering your question, looking at signals or random processes in the frequency domain can help us solve problems. For instance, this problem is very difficult to solve in the time domain. how can I find a signal H that will do, that will, when I convolve it with itself and shift it, it will give me that. It's some kind of, people talk about some deconvolution of this and something like that, but it's a difficult problem to solve. Okay? Questions? Okay, so we have seen so far the Bernoulli-Radon process, the Poisson-Radon process, White's and stationary and strict stationary processes in general. Let me define also a Gaussian random process. So what is a Gaussian random process? X of t, t in R, is a Gaussian random process if every linear combination z equals summation I 1 to n of ci x pi is Gaussian random variable. What does that say? X of t is a Gaussian random process if any time I pick n samples out of this random process, any n samples I pick, no matter what n is, 1, 2, 3, 100, a million, finite, at any point t1, t2, t3, all the way to tn, these random processes are jointly Gaussian. That's another way to say that. Because what is the definition of n random variables being jointly Gaussian, x1 to xn? How did we define jointly Gaussian random variables?
With the same summation.
If any linear combination of these random variables is a Gaussian. That was our general definition, right? And so here this says that a random process is Gaussian if any sample, any number of samples you take, are all jointly Gaussian random variables. That's it. Okay. One such Gaussian random process is, example 1, is white Gaussian noise.